Hello folks, this is Dr. Young, and in this video I'm going to introduce some of the reactivity of carbonyl compounds. We're going to take a look at a few, and specifically we're going to look at the reactivity towards nucleophiles. Now there's other reactivities like towards bases or acids and other things, but this is mostly going to be about nucleophiles. So just to make sure we're on the same page, right, we're talking about carbonyl compounds here. So we've got like things like aldehydes, ketones, esters, amides, carboxylic acids, anhydrides, acyl halides, carbonates, carbamates. There's all kinds of carbonyl compounds. Here's just, 5 of the most common ones, right? And just to jog our memory, right, remember aldehydes are something where you have an H attached to the carbonyl. Ketones are when you have 2 carbon groups attached to the carbonyl. Esters, you need to have an oxygen, but then some other carbon group. So, and then this can be whatever. So you're going to have an O and then another carbon group. Amides are similar to esters, only it's a nitrogen directly attached to the carbonyl instead. And then carboxylic acids, right, are where you have a carbonyl and there's an OH attached to it. And again, just to make sure we are on the same page here, by carbonyl, right, we're talking about the C double bond O. So carbonyl just means a C double bond O. So it's part of a lot of different functional groups, right? We see the carbonyl in aldehydes, we see the carbonyl in ketones, we see a carbonyl in esters, and amides, and carboxylic acids, and other functional groups. But again, these are just some of them. So the reactivity, like I mentioned before, that we're looking at here is we're going to talk about the reactivity of a carbonyl, some generic carbonyl here, and I'll draw a line. We're talking about the reaction between some generic carbonyl, and so I'll just leave it as 2 R groups. So this might be a ketone, for example, and a nucleophile, right? And so with our nucleophile, right, we know that they're partially negative or fully negative. If I look at my carbonyl compound here, oxygen is more electronegative than this carbon is, so it's partially positive. So I got my little delta plus, delta minus. And so our mechanism, right, for a lot of these reactions that we're going to talk about in the next coming chapters, right, when we're talking about additions to carbonyls, so ketones and aldehydes, is that the nucleophile is just going to be attracted to this carbon, and you're going to kick up and break this pi bond, right, which means that we're going to end up adding a nucleophile to our compound. So now you'll have an O minus and an R group, and then your nucleophile will be attached. And then we'll see later that usually there's a protonation step to turn it back into an alcohol, but I'm just going to leave that blank for now. We'll come back to the actual specific reactions later. But just the general addition mechanism, right? We're just adding something to a carbonyl. Before you didn't have a nucleophile attached, now you do have a nucleophile attached. So we just added something. Now, we do need to say something a little bit about MO theory, right? Our molecular orbital theory stuff. If you look at these generic carbonyls, and you're looking at the HOMO and the LUMO, those frontier orbitals, right? The highest occupied molecular orbital and the lowest unoccupied molecular orbital. They're going to have to do with the carbonyl. So we want to look at, we're going to look at the C double bond O molecular orbitals, specifically the pi bond, because that's going to be the higher energy one, right? Pi bonds are higher energy than sigma bonds, generally speaking, especially for things like ketones and aldehydes. So we're going to look at the pi bond of the carbonyl, right? So if we have a CO, and let me just draw this out. So we're just going to have a CO. And if I take a look at the pi bond here, what I'm going to do, my class has definitely talked about this before. I'm not sure if this is quite registered with everybody, but if we're talking about the pi bonds, right? So I'm going to draw the pi here. And we talked about before. Let me back up. Let's say just generically, right? Let's remind ourselves what a pi bond looks like. So for a carbon-carbon pi bond, right? Remember we said that, oh, well, you have 2 pi orbitals. When they line up in phase, they overlap to give you a CC pi that looks something like this, right? This would be your pi bond, your pi orbital. And then similarly, if you had a CC and you had the antibonding orbitals, so you have them line up so that they're opposite, so you have the destructive interference instead of constructive like above, then you get sort of this more butterfly-y shape thing where you have your pi star because you had the destructive interference, right? That's supposed to be a star. I can draw a better star. Now, this is going to be versus a pi bond for a carbonyl. One thing to keep in mind when you're drawing MOs, if you have things that are of different electronegativities, that the same orbital on the more electronegative element is lower in energy, right? So with two carbons, those two p orbitals, they have the same energy as one another. But if you look at the p orbital on a carbon and an oxygen, the oxygen actually has a lower energy than the one on the carbon, and that's because it's more electronegative, because those electrons are going to be closer to the nucleus, so the electrons are more stable, right? Hence the lower in energy. So like, what does that kind of mean for us? What that means for us is that when I go to combine, let's see, when I go to combine the p orbital of the carbon and the p orbital of the oxygen, that what ends up happening is that it ends up being lopsided on the oxygen's side. So what I mean by that is, notice how over here it's sort of evenly distributed on the CC, right? So this pi is evenly distributed, right? There's not one, neither one of these carbons has more of the pi bond than the other one. That's not lopsided, right? Or in other words, we can say that this is nonpolar. What we're going to see for when you have two things that have different electronegativities is that it's not going to be evenly distributed. It's going to be lopsided. So now my pi bond is going to be similar, but it's going to be kind of, like I was saying, lopsided. So this is my version of lopsidedness. It's still a pi bond, but it's supposed to be lopsided. It's supposed to be on one side versus the other, right? So now we have lopsided. It's an unequal sharing or uneven sharing, right? Which means that this is going to be, I don't want to draw a star too close to that pi. That's not a pi star, it's just a regular pi. What that means, right, is that this leads to a polar bond, right? And we know that, like I just drew up there, right? I drew up here that there's a partial negative on the oxygen and a partial positive on the carbon. We know that that's the case, right? And I'll even add that here, partial negative here, partial positive here. And that's just because most of the electrons are hanging out on the oxygen side, not the carbon side. So you get that little dipole thing. Now what we see is that we see that also kind of plays with the anti-bonding orbital. So when they line up out of phase. So let me draw these, and I'll draw them out of phase this time. So it's going to be the same but opposite. So in the bonding orbital, they're lopsided towards the O, but in the anti-bonding orbital, they're going to be lopsided towards the C. So I'm going to draw kind of like, it's going to look kind of like the CC pi star that I drew on the left, but I'm going to draw it with the COs now, and it's going to be lopsided in the other direction. So I'm going to have a bigger lobe of the pi star on the carbon and a smaller lobe of the pi star on the oxygen. And so it's also lopsided, but again in the opposite direction. So in the pi, it's lopsided towards the O because it's more electronegative, but in the anti-bonding, it's the opposite. It's going to be the carbon side that is larger. So like, why is this important? Why do we care? Remember that when you attack something, right, when a nucleophile attacks something, it goes into an empty orbital. And both of these are empty, right? It's the pi stars that are empty, right? This is empty. This is empty. Whoop, this is empty. Right? So that's the pi stars that are empty, so it's the pi stars that get electrons put into them. And that's important to know because that means that our nucleophile, when it attacks a carbonyl, what it does is it dumps electrons into these big old honkin' back lobes on the carbons, right? So we've got these big old empty pi star orbitals on the carbons that the nucleophile attacks. It doesn't attack, and it doesn't really attack at a 90-degree angle, right? You can actually look at that. There's a specific angle. We don't have to go over it, but there's a specific angle here, right? It doesn't come at 90 degrees at the carbonyl carbon. It doesn't come in directly from the back. It comes in a little bit from the top. It's kind of almost a 45-ish degree angle that it attacks the carbon. And I'll show you why that's important later. But yeah, when you attack a carbonyl, you're going to come at it from an angle and you hit that pi star. And I'll draw another one of these when we talk about the sterics here in a second. So when we're talking about electrophilicity, we need to talk about two factors, electronics and sterics. So, right, electrophilicity just talks about how quickly you're going to react with the nucleophile, and right, we want to remember that nucleophiles, right, tend to be negative or at least partially negative. And so the electronics that we're caring about here, right, is just that it needs to attract the electrophile, right? So we need partial positives or really big positives, right? So, or in other words, the more positive, right, the more electrophilic. Or in other words, we want it to be more electron poor, right? We want it to be electron poor. If it's electron rich, it's not going to attract a negative nucleophile. If it's electron poor, it is going to attract a negative nucleophile. So let's take a look at these aldehyde. I have an aldehyde ketone ester and an amide here. So let's just compare the aldehydes versus ketones, right? And so what we're going to take a look at here is I just want to look at what is going on, which of these carbonyls is the most electron rich or poor, right? Because I've got that carbonyl, this carbonyl, this carbonyl, and this carbonyl. And so if I compare, for example, just the aldehyde versus the ketone, the aldehyde just has H's on it, right? They're kind of boring. They don't really do anything. They don't withdraw. They don't donate electrons. But the ketones, right, they have this one here, for example, has a CH3 and a CH3. Remember that ketones are all alkyl groups are weak electron donors. So they actually donate in electrons weakly, right? Remember that alkyl groups are weak electron donors, right? Are weak electron donors. That's a key thing, right? Just like with we talked about with electrophilic aromatic substitution, just like if you're dealing with acid-base stuff, right? Alkyl groups tend to be weakly electron donating because of hyperconjugation. Same thing is true here, same principle. So between the two of these, just aldehydes or ketones, I want to know which one's more electrophilic, or in other words, which one's more electron poor. And if I look at these two here, right, if I'm comparing just the aldehydes and ketones, the ketones have donating groups, which are making the carbonyl more rich, right? So I'll add that note too. So alkyl groups are weak electron donators, and the effect of this is that the carbonyl is more electron rich, right? It's more electron rich. So if I compare the aldehyde versus ketone, all aldehydes and ketones, all aldehydes are more electron poor. Ketones are less electron poor, right? Because they're having electrons being donated into them, which means that aldehydes are better electrophiles, right? They're going to attract a negative nucleophile better than a ketone. So compared to a ketone, this is a worse electrophile than an aldehyde, just because ketones are a little more electron rich, so they don't attract those negative nucleophiles as much. And again, they're more electron rich because they have alkyl groups which donate electrons. Now, if I go and I look at my esters and my amides here, right? So if I go and I look at this ester, yes, I have an alkyl group here, but then I also have an O. And the question is, what is that O going to do? And again, we're going to think back to kind of like what we did for the electrophilic aromatic substitutions when you had your donators and withdrawers, your activating groups and deactivating groups. Same ideas here, right? We said that an O attached to a phenyl ring acted like an electron donor because of resonance, right? Because of electron delocalization. Same exact thing here, right? Because I can draw electrons dropping down and kicking up, right? I can draw a resonance structure with this where I've got O minus, double bond O, got my ethyl piece still and a positive, right? I have these resonance structures. This O then is considered a strong electron donating group, right? So the O, this OR group, right, is a strong electron donor. Which means if I compare it to the ketone, that this is even more electron rich than the ketone, right? Which means this is more, sorry, that's supposed to be an arrow symbol, more electron rich than a ketone, right? Because a ketone just has the weak donors on there, right? Just the alkyl groups. But an ester has a strong electron donor on that carbonyl, so that carbonyl is more electron rich. It's got more electrons than the ketone does, which means that my esters are even less, I guess I'll say even less electrophilic, right, than the ketones are. They don't react as quickly because they're so electron rich, they don't attract that negative nucleophile as much because of that. And if we go and we look at the amides or amides, same deal, right? So this particular one, yes, it has a weak electron donor on it, but it also has a nitrogen, which also can donate electrons and also kicks up electrons. So I'll draw its resonance structure also. Minus, here's my two resonance structures, my resonance arrow. So it looks like the nitrogen also acts as a strong electron donor, right? Just like, again, like we said with the aromatic stuff, right? Anything with a lone pair attached to that phenyl ring was a strong electron donor, a strong activating group. Here it is a strong electron donor. It's just the opposite. We're not activating the carbonyl here. We're actually deactivating the carbonyl. But yes, it's donating electrons down, kick up. We got that resonance structure. So the N, right, the amines, whatever the amines are, so I'll just put NR2, is also a strong donor. But the question is it a stronger donor than the O is, right, than the esters? So if what I want to look at then is compare the relative stabilities of those resonance structures, right, those resonance contributors. Obviously, the uncharged top ones are the more stable resonance contributor, the major, and then the charged ones on the bottom are the minors. But the question is, which one is seeing more, which one is a better contributor for the actual structure, which one's actually donating more? And to do that, right, to make that comment, we just have to look at which one's more stable. So I want to ask myself, what are you more likely to have? A positive O, so I'm comparing the stability. I'm comparing the stability of a positive O versus a positive N, right? Because whichever one is more stable is going to be the larger percentage contributor to the ester or the amide, respectively. And we should all remember, right, that oxygens are relatively electronegative, right? They're very electronegative. They want to be negative, not positive. Nitrogen's further away, it's less electronegative, which means it's more stable being positive. So between the two of these, the nitrogen is more stable, is a more stable positive, which means this is a better contributor. I'm going to run out of room. Better contributor, right? It's a better resonance contributor. So it donates more. It is a stronger donor, right? Because that resonance structure is less absurd, it is a larger contributor to the real structure of that compound, which means it does donate electrons in more than if it was an O minus, or than if it was an O plus. So what I'm going to put here is that the NR2 is the strongest of these three, is the strongest electron donor, right? It's much stronger than just an alkyl group because alkyls are just hyperconjugation. It's just like kind of like inductive stuff, not resonance. And then of the two that have resonance, they have the delocalization. The amides have more of a contribution because N is more stable being positive than O is stable being positive. So the N2 is the strongest electron donor, which means this is the worst. This is the worst electrophile that we have up here. Amides are super unreactive to electrophiles. You really have to heat them up like crazy. You have to use strong bases typically. I mean, you always have to use strong bases. You usually have to heat them up. They're much, much slower than aldehydes, ketones, or esters. And it's just because they're more electron rich. This is all just electronics. It's just looking at resonance structures. So let's take a look at sterics, which is much more straightforward. So for sterics, right, we're just talking about electron repulsion. Because again, like I was saying before, and I'll draw this out here. If I just let's just take some sort of generic ketone thing. I'll draw a double bond O. And I'm going to try to draw this flat looking. So I'm going to draw a wedge for like one R group. and then the dash for the other R group. So this is supposed to be looking at it kind of sideways, so not straight on flat, but a side view. And again, if I put those MOs, right, we said we're dumping into the pi star. And the pi star, again, looks like this. It's sitting up on top of the carbon and below the carbon, and then a little bit on top and below the oxygen, where we have different phases here. So it sits above and beyond that plane, right? So you have the flat trigonal planar shape of in this case, a ketone or something like that. And then sticking above and below that is your pi star. All right, this is our pi star that I'm drawing, the empty pi star. So, and again, if we take our nucleophile here, we're saying that our nucleophile, it doesn't attack, right? So let me do, well, I'm going to erase this, so just keep that in mind. It does not attack, right, in between the two R groups, right? There's no orbital there. It doesn't attack like where the carbon, where the CO double bond is, because again, there's no molecular orbital there. What it does is it attacks one of the lobes of those pi stars. So let me erase the incorrect drawings, fix my R. What we do see that the nucleophile does is it adds into that empty pi star, right? That's what puts electrons in the antibonding orbital and breaks that pi bond. So you have a CO single bond. So it's so the sterics do matter, and it does come kind of where those R groups are. So the bigger those R groups are, the harder it's going to be for your nucleophile to get to those orbitals. So sterics plays a big role. You can imagine, right, if we have these really tiny groups, right, these are very small, very unhindered. So very unhindered, sorry, I can write that better. So for just this little guy, formaldehyde, right, these are just hydrogens. These are just hydrogens. So this is very unhindered. Now it's much better. Look at that. Very, very unhindered. You can imagine now, right, now that I'm adding an isopropyl group, there's a lot more sterics there, right? Now I've got this relatively large isopropyl group. This is going to be much more hindered. Much more hindered than if it's just hydrogens. T-butyl groups are bigger than isopropyl groups, so we're getting even more hindered. Even more hindered. And then as you can imagine, if you had, right, two isopropyl groups, so now we have a ketone, that's even more hindered, right? So this would be the most hindered. The most hindered of these carbonyls. Of these carbonyl compounds. And then to kind of make sure we're speaking the same language, in terms of electrophilicity or the speed of a reaction with the nucleophile, right, this would be the slowest. This would be the slowest, least electrophilic. And this would be the fastest, most electrophilic. And you may have heard, for example, just to kind of bring this into things that you're aware of, you may have heard of this molecule before, right? This is formaldehyde. You probably know formaldehyde for bad reasons, right? It's toxic. It's used in what's it called? It's a fixing agent for when you do like not taxidermy stuff. You put stuff in jars. You know what I'm saying? Word's not coming to me right now. But formaldehyde, right? That's the stuff that helps fix. It's a fixing agent. It's toxic. It's used in a lot of glues, or has been used in a lot of glues. They're kind of trying to phase it out. But one of the reasons why it's used in glues, why it's so good at gluing things, and why it's so good at preserving things, you know, as a fixing agent, is because it's such a good electrophile, right? Formaldehyde is a great, too good. It's a great electrophile because it's an aldehyde, which means it's very electron poor, so it's very easy for nucleophiles to add into it. Also, it's very tiny, so again, it's very, very easy for electrophiles to add into it. And that's a problem for you and me and all living things, is because if we get that in us, we've got loads of nucleophiles in us, right? We've got proteins, we've got DNA, we've got all kinds of things that are nucleophilic that will add to formaldehyde, and formaldehyde will stick to. So it's a very toxic little compound because it's so electrophilic. It is just too, it's too much, it's just too much for us. It's too electrophilic, it just reacts as soon as it touches us. Versus if you get things that are bigger, they become much less electrophilic and are not really problems, right? Like vanillin, for example, is much bigger. Vanillin is not exactly the most toxic compound in the world. So let's combine both of these together and look at an example. So let's say, right, that I want you to rank these in increasing reactivity with a good nucleophile. And in this case, I'm saying something like CH3-MgBr, which is a Grignard reagent, which is something we're going to learn about in videos coming down the line. But I'm just giving you an example of a specific thing that this would be true for. You may come back and watch this video again, or you may come back and look at your notes again and be like, oh yeah, Grignard reagents, methyl Grignard. Yeah, I remember that. But it doesn't matter what the nucleophile is. This is just general in terms of reactivity. So again, we want to consider two things, right? We want to look at both what is it an aldehyde, ketone, ester, etc. And so I'm going to look at this. I'm just going to go ahead and name these all, right? So this is an amide. I know that's an amide. This is a aldehyde. This is a ketone. This is an ester. And this is another ketone. Sorry, you should probably pause and try this yourself. I'm just so excited. I want to go ahead and do it, but you should probably pause, see what you can do yourself, fill in the bottom slowest to fastest reaction with an electrophile, and then come on back with me and take a crack. Okay, hopefully you actually tried it so that you exercised your brain some. But if I'm looking at these, right, I see amide. I remember the amides are really, really unreactive. They're the slowest because they're such electron-rich carbonyls, because that nitrogen donates electrons in so well. And I remember that aldehydes are my fastest ones. So I'm just based on that, I'm gonna start with that. I'm gonna start with that and say, okay, well, I know that aldehyde here, I only have one aldehyde, so I think my aldehyde is gonna be my fastest. So I'm gonna put that as my number one, so that's B. And then amides I know are the slowest, just in terms of these functional groups. So I'm going to go ahead and put that as my slowest reaction. And then of these three that are remaining, C, D, and E, I got two ketones and I've got an ester. And I know that the ester is slower than ketones. So I'm going to put that as my second slowest one. And then I've got two ketones, which are equal in terms of electronics, right? So far I've just looked at electronics. But the big difference between these two, right, is the sterics. Here on this ketone on the left, I've got a primary group on the left, and I've got a methyl group on the right. And here on my E, I have, again, a primary group, but on the right, I have a secondary group. So if I look at E, this one's just more sterically hindered. There's just more steric interactions. So more sterics, and then fewer steric interactions. So between these two, I think that E should be slower and C should be faster, just based, again, like I was saying, on steric issues. So if I put that all together, I think that C should be my second fastest and E should be my middle one, right? So we should be able to look at a carbonyl compound and decide, is it relatively electrophilic or not? Because, for example, in like a next video, I'm going to show you some reagents only work with really reactive carbonyls, so namely aldehydes and ketones, and they don't work with the harder ones, so like esters and amides, for example. So go ahead and take good notes. Let me know if you have any questions. Good luck studying.